Fracture analysis of plastics uses fractography, examining fracture surfaces with optical and scanning electron microscopes to determine how and why a part failed, identifying mechanisms like ductile, tearing, deformed, versus brittle, sudden, flat, failure, fatigue, creep, or environmental stress cracking. By analyzing surface features, mirror, mist, hackle regions for brittle fractures, and correlating them with material properties and service conditions, engineers pinpoint root causes like overloading, material defects, design flaws, or chemical exposure to prevent future failures. Fracturing of plastic molded parts occurs when the molded part can't endure the impact load beyond the plastic material's limit strength. As such, fractures occur in various ways, influenced by applied plastic materials, design of molded parts, operating conditions, external circumstances, and so on. Fractography, the primary technique involving visual and microscopic examination of the broken surface to find clues about the failure. Special Surface Observing Equipment, SEM, scanning electron microscope, is most often used in observing the fracture appearance minutely for understanding specific causes of fracturing. Common fracture modes are ductile, brittle, fatigue. Besides these, there are creep and solvent cracking. Ductile fractures. Ductile fracture involves significant plastic, permanent deformation, necking, and high energy absorption before breaking, with rough surfaces and warnings like dimpling. Usually, the material undergoes necking before breaking. Large deformation of the resin causes fracturing. The characteristic shape of the fracture surface is called the dimple pattern. Brittle fractures. Brittle fracture happens suddenly, with little to no deformation, low energy absorption, flat, shiny surfaces, and no warning, typical of glass or ceramics, though metals can become brittle at low temperatures. A brittle crack often starts at pre-existing defect, such as void or inclusion and high stress concentration. Almost no deformation of the resin. Cracking progresses rapidly, leading to fracturing. Even ductile materials can develop brittle fractures due to factors such as load conditions, environment, etc. The characteristic shape of the fracture surface is called the river pattern. Brittle fractures appear differently depending on the degree of stress concentration. These changes can also be used to identify the cause of fractures. River patterns, named because they resemble a flowing river, are caused by crack propagation. They are characterized by spreading radially from the crack area, so you can identify the crack area by searching for the region at which they converge. Fatigue fractures. After repeated loads, a cross-sectional reduction associated with crack onset and development leads to fracturing. Since plastic deformation is limited to the proximity of the crack progression path, it has a brittle appearance. The characteristic shape of these fractures is called striation. Fracture shape. The transverse lines, shaped like tree rings, are observed at the surface of fracture appearance. Cause. The part's fracture occurs due to the stress by periodic vibration and operation. Feature. It takes for a long time to incur the fracture. Creep ruptures. Deformation occurs over time when under constant load stress, leading to fractures, especially at high temperatures. Fine stretching is observed in the resin. Fracture shape. Observed tiers of resin at the surface of fracture appearance. Cause. The fracture occurs after enduring consistent external force. Solvent cracking. Cracking occurs due to stress and environmental factors, chemicals, etc. Also called environmental stress cracking, chemical cracking, etc. Fracture mechanism. The fracture surface can be analyzed by optical and electron microscopy in different zones, initiation, propagation, arrest, in order to propose cracking scenarios related to the microstructure of semicrystalline polymer. In the arrest zone, the microcracks developed upstream continue to propagate in different directions. Fracture of solids is, generally speaking, a process of development of discontinuities flaws which may be pre-existing and/or nucleated in the material structure during the early stages of deformation. In the immediate neighborhood of the crack front, a prefracture region is formed where weakening and rupturing of cohesive bonds occur. These processes occurring on atomic scale are beyond the scope of continuum mechanics. The prefracture region is usually enclosed by a zone of plastically deformed material. The deformations in this zone govern, to a great extent, the processes of prefracture and define the modes of fracture of a body. Depending on the size of the plastic zone, brittle, quasi-brittle, and ductile fractures are differentiated. Almost all the energy consumed in fracture consists of the energy dissipated in the plastic zone, and only an insignificant part of it is spent in breaking bonds. Thus, studies of plastic DC formations around cracks appear to be of fundamental importance for describing the process of failure from a macroscopic standpoint and constituting criteria of fracture. Initiation and propagation are considered to be controlled by the extent of total plastic shear deformation. Crack initiation and crack propagation occur when deformation exceeds a critical threshold value, which can be equated to threshold conditions determined from linear elastic fracture mechanics analyses. The appearance of micro and macro cracks is largely correlated to the microstructure and heterogeneities of the material, the mechanical stress, or even the effects of the environment. The fracture behavior of polymeric materials has been extensively studied in the literature. Environmental effects, temperature and strain rate, for example, can significantly modify the emerging behavior of the material. By increasing the strain rate, a polymer can change from a viscoelastic plastic ductile to an elastic brittle behavior. Studying the resistance to initiation, or slow propagation, or to rapid propagation can be significantly different for the same polymer material. Homalite 100 and polymethyl methacrylate, PMMA, have regularly served as model materials for studying materials with brittle linear elastic behavior. Their fracture facies have been widely described. Different characteristic zones exist. At crack initiation, conical markings can be observed. They result from the interaction between a macro crack front and micro crack fronts that develop downstream of the main crack. The analysis of these marks in terms of density and size makes it possible to estimate the crack velocity. During the rapid propagation of the crack, the fracture surface is known as a hackle zone. This zone is chaotic in terms of roughness. Microbranches, as the origin of non-trivial roughness, develop from a critical speed. Between these two zones, initiation and propagation, there is an intermediate zone called mist. For Homalite 100, it is established that in the mist zone, several small cracks propagate simultaneously, and the front of the overall crack is almost straight. In the hackle zone, crack growth occurs by the same physical process as in the mist zone, except that the size scale of the microfracturing increases. For PMMA, it has been observed that in the hackle zone, and for cracking speeds above about 500 meters per second, the fracture surface becomes very rough with periodic microbranch-induced marks. They generate arrest marks spaced about 1 millimeter apart, commonly called ribs markings, because of their geometrical shapes. The high roughness observed in the hackle areas is generally not taken into account in the estimation of the fracture energy. It is nevertheless admitted that the higher the energy release rate, the rougher the fracture surface is. Fragmentation of degraded plastics and release of smaller secondary microplastics is usually attributed to the growth of environmental stress cracks. Analysis of crack patterns derived from chemical degradation can be useful not only for assessing the cause of plastic fracture and evaluating the useful lifetime of a product, but it can also potentially provide valuable information on the generation of microplastics.